Hello and welcome to another tech video on my channel. In this video, we are going to implement a 3-tier architecture on AWS using Terraform infrastructure as code. I have already created a separate video on the 3-tier provisioning using the AWS console. I will recommend you to watch the video before jumping onto the Terraform implementation. I will mention the link in the description as well as the I button. If you are already comfortable on the console, you can skip that and continue with this video. Many people had requested this Terraform implementation. It was a long overdue from my side. So without further ado, let's head on to the implementation. So let's first understand the architecture we are going to deploy via Terraform today. Under the AWS cloud, we are going to deploy the entire infrastructure in the North Virginia region or the US East 1. The networking services we are going to provision are VPC. Then we are going to configure availability zones. Those are US East 1A, US East 1B and US East 1C. We will have 3 public subnets, each in one availability zone. Similarly, we will have 3 app subnets and 3 database subnets. Moving to infrastructure components, we will have application load balancer deployed in multiple availability zones. I have shown here in between 2 availability zones, but we can configure across 3 AZs as well. Then the PHP servers configured in an autoscaling group. And finally, RDS MySQL instance, which is deployed in one of the AZs. I have grayed out the multi-AZ as it is optional. If your application demands, we can set up multi-AZ as well. I will demonstrate the option to configure that while explaining the code base. Before we begin, let's understand what we are going to learn from this video. We will see the standard file structure and the naming convention. We will learn how to write clean, externalized and reusable code in Terraform. Then we will learn how to define and declare variables in Terraform. Then consuming the official AWS Terraform modules. This is important because we don't have to reinvent the wheel and recreate what is already there. We will also learn setting up a remote backend. This is required to externalize your state file for potential state losses and also to support multiple people working on the same project. Additionally, we will also implement state locking. I have already created a detailed video for this topic. I will add the link here in the description and as well as the I button. Then we will learn how to define outputs in a Terraform project. And finally, we will see some of the Terraform best practices along the way. Before we proceed further with the hands-on demo and the implementation, there are several prerequisites which you should know, which will help you to understand the implementation better. Under AWS, you should have a basic understanding of VPCs. Within VPCs, you should know public and private subnets, security groups, NAT gateways, and the internet gateway. Along with VPCs, you must also possess basic knowledge of EC2 instances, EC2 autoscaling, and the application load balancer. To understand the 3-tier in detail, you must also have basic information on RDS. To complete this exercise, you should also know how to install and configure AWS CLI on your local machine. So this was about AWS knowledge. Moving further with Terraform, knowledge of infrastructure as code and HashiCorp configuration language is needed. Apart from that, the understanding of Terraform module is also required as we are going to consume the official AWS modules from the Terraform registry. And finally, you should be able to install and configure Terraform locally. Let's have a look at the environment which is already set up. I have already logged into the AWS console and selected North Virginia as the region. I have provisioned the S3 bucket to store the state file. In addition to that, I have also created a DynamoDB table to store the locking information. We will talk about this during the code walkthrough and implementation. As mentioned in the prerequisites, AWS CLI is already installed on my machine. Here is the version number for your reference. Terraform is also installed and configured locally. This is the version information for the same. Now let's see how AWS CLI can be configured for your account. To configure the AWS account, you need to execute the command aws configure. It's already done for my machine. Hence, you see the access key information. Enter your access key ID and press enter. Enter the secret access key. Enter the region name. I have chosen US East 1, that is North Virginia, and then press enter. And finally, enter the output format of your choice. I am comfortable with JSON, hence I have added the same. That was it for the environment configuration. Let's proceed further with the code walkthrough. Before we begin, you can skip this part if you don't want a code walkthrough. I recommend you to complete this walkthrough as well because I have tried to explain the code and its purpose in detail. Anyways, I will provide the GitHub link for this code in the description. I have opened Visual Studio Code on my machine. You can use any IDE of your choice. Let's first open the versions.tf file. This file contains all provider and version information that we are going to use in our Terraform project. Each Terraform module must declare which provider it requires so that Terraform can install and use them. Provider requirements are declared in a required_providers block. A provider requirement consists of a name, a source location, and a version constant. The source is HashiCorp/AWS and the version is any version in the range 4.0. Tilde allows only the rightmost version component to increment. So here 4.1, 4.2 and so on are permitted. The provider configuration is created using a provider block. Here we have only one configuration, that is the region. So all the resources that we are going to provision will be created in the US East 1 region. Next is backend.tf, which holds all the configuration related to your backend for storing state files. To configure a backend, add a nested backend block within the top level Terraform block. Inside the backend block, we have bucket parameter where we will enter the S3 bucket name which we had created earlier. Encrypt parameter is optional. I want to have encryption enabled, hence I have set it as true. Key is the name of the object to be created in the S3 bucket. Region is the AWS region where state file will be stored. And DynamoDB table is for passing the table created to store the locking information of the state file. As mentioned earlier, I have created a detailed video on the S3 backend and locking. Link is mentioned in the description. The next file which we are going to look at is the variables.tf file, which has all the variables declaration in it. A single variable declaration has description, type and default value parameters. As a best practice, all variables should have a default parameter. We have declared variables for all infra components here. These are VPC variables, then autoscaling group variables, application load balancer variables, and finally the RDS variables. We have seen the declaration. Now let's see how we can define them in Terraform using the terraform.tf vars file. In this file, we see all generic variables, autoscaling group variables, ALB variable, and RDS variables which were declared in the variables.tf file. For example, the VPC name which we see here is declared in the variables.tf file under the VPC section. All supporting files are done. Now let's move on to the core infrastructure files. First, we will see the vpc.tf file. So here we are not creating our own resource code. Instead of reinventing the wheel, we are going to consume the ready-made module from the official Terraform registry for AWS. The benefit of using modules over resources is the reusability of the code and the maintenance efforts which we are going to save. The developers of the modules will develop the code and provide updates to the code. So here is the entire module block with the relevant parameters. Let me run through all the parameters quickly. First is the source from where module code will be downloaded and consumed. Then the module version, the CIDR ranges to create the VPC, availability zones, private subnet CIDR ranges, public subnet CIDR ranges, database subnet ranges, boolean to create a database subnet group, boolean to enable host names, boolean to enable the DNS support, boolean to enable NAT gateway, then single NAT gateway. This parameter, if set as true, will create a single NAT gateway, or else it will create NAT gateways equivalent to the number of availability zones. Let me also quickly show you from where we have consumed this module from the official documentation. I will provide the link in the description. These are the provisioning instructions, the source code GitHub link, and you can choose examples from here. After VPC, let's see ALB. For ALB, we will require supporting resources, that is security group. Even for security group, we have an official module. We will see a similar kind of a module block with source and version information and other parameters. VPC ID will have the generated VPC ID from the VPC module. Ingress CIDR block is the IP address range from where we want to allow access to the load balancer. This module is consumed from here. I will provide the link in the description. Now let's look at the actual module code for ALB. Again, here we see source and version parameters, VPC, subnet, and security group information. Security group is referred from the module on the top. Then we have TCP listeners parameter and target group parameters. Here I have commented the stickiness parameter. I will talk about this in detail during the demo. To understand all these modules, you should have implemented the VPC, ALB, ASG and RDS manually using the AWS console. The module is consumed from here. I will provide the link in the description. After ALB, let's quickly see the module for ASG. In this module, we will use the user data to install PHP stack and configure phpMyAdmin. Please read about EC2 user data if you don't get the implementation. Let me run through the user data steps. We'll do a yum update, install PHP libraries, install Apache, start Apache, enable Apache, add user to the Apache group, add group right permissions, install some more PHP libraries. This is required for phpMyAdmin. Do an Apache restart, restart PHP FPM, get into the HTML folder, download phpAdmin files, create a phpAdmin directory and untar the files in the same, remove the tar file, create file phpinfo, get into phpMyAdmin folder, rename the config file from the config.sample.inc.php to config.inc.php, and finally replace the string localhost with the RDS hostname. This is required for the phpAdmin to connect to the RDS instance. Moving forward with the supporting resources, we will require a security group, source, version and other parameters will remain the same as previously shown modules. Here the security group information is little different from the previously created one for the ALB. As this requires ALB security group as source for port number 80, for ALB it was a CIDR range. I will add the module documentation in the description. Now let's move on to the auto scaling group module. I won't be explaining each and every parameter here or else the video would become a really long one. You can refer to the official module documentation for all the parameters. I will provide the link in the description box for your reference. All the variables that you see here are declared in the variables.tf file and defined in the terraform.tf vars file. The user data that we see in the locals is used here in the line number 75. We have used the native base64 encode function and passed the same. Apart from that, we have mapped two block devices as seen here. The volume sizes are taken from the terraform.tf vars file. And the network interfaces are defined here with the security group attached created in the earlier step. Here is the document for this module. You can see all the input parameters here. And finally, let's look at the rds.tf file. For RDS as well, we will create a separate security group. All the parameters will remain the same as the ASG security group and then the actual RDS module. Again, I will not discuss each and every parameter in detail. All these parameters are defined in the RDS section of the terraform.tf vars file. If the multi-AZ parameter is set to true, RDS will create a failover instance in the other availability zone. I will mention the link to the official documentation in the description below. And finally, the last file we will understand is the outputs.tf file. So here are the outputs defined for the VPC. An output block will have a name, description, and a value parameter. An easy way to get the list of outputs would be referring to the official documentation of that particular module. In this case, these are the outputs for the VPC. So to gather the outputs code, go to the GitHub repo for the module. Copy all the relevant outputs you need and add it in your outputs.tf file. Similarly, we will have outputs for autoscaling group, application load balancer, and relational database service or the RDS. So we have covered all the files and their purpose in detail. Now let's move on to the actual implementation. Right click on the Explorer section, open the integrated terminal. In the terminal, execute Terraform init. The Terraform init command initializes a working directory containing Terraform configuration files. This is the first command that you should run after writing a new Terraform configuration or cloning an existing one from the version control. So whenever you try to run this command, it will try to download the modules consumed in your Terraform configuration files for the provider. So here we see it is downloading ALB, security groups, autoscaling group, RDS and VPC module that we saw previously during our code walkthrough. It says successfully configured the backend S3. Now we see that the Terraform has been successfully initialized. Now let's do a Terraform plan. The Terraform plan command creates an execution plan which lets you preview the changes that Terraform plans to make to your infrastructure. By default, when Terraform creates a plan, it reads the current state of an already existing remote objects to make sure that the Terraform state is up to date, compares the current configuration to the prior state and noting any differences, proposes a set of change action that should, if applied, make the remote objects match the configuration. As soon as you execute the plan command, it will acquire a state log so that no one else can make changes to your state file in case multiple people are working with the same infrastructure. This is the plan that Terraform has generated. Some of the infra details will be known only after the apply command. As soon as your plan is finished, Terraform will release the log which was acquired previously. If you want to save the output of your plan command for future references, you can do that using the out parameter. This output file can be passed into your Terraform apply command. Usually this is used during the Terraform automation. And after plan, let's execute the Terraform apply command. Here again we can see that it is acquiring state lock so that no one else can make changes to the state file during the execution of this command. Once the command is run, it will prompt the user to enter yes as a confirmation to the Terraform script onto our infrastructure. I will wait for the provisioning to complete the infrastructure creation and resume once it is completed. So after waiting for about 14 minutes or so, our infra creation was successfully completed. The creation took so much time primarily because of the RDS instance. Generally, the RDS instance creation is a time-consuming process. So here we see apply complete, 51 resources were created, and since it is a fresh implementation, no resources were changed or destroyed. And we will also see the outputs that apply command has generated. So the implementation is complete. Let's see what all changes the code has made to our AWS infrastructure. It has created a Terraform TF state file in the S3 bucket. Let's try to open that file. And you will see a use list of resource information and its metadata. In the backend.tf, apart from S3, we had also configured a DynamoDB table to store the state information. Let's have a look at it. In the DynamoDB table, under explore items, we see an entry which was created during our execution. If you want to understand a detailed workflow for Terraform remote backend, I have already created a separate video on the same. I will provide the link here in the I button as well as the description. Now let's see what actual infrastructure it has created. Go to VPC. You can see here a demo VPC is created. It has configured VPC as per what we have passed in the module parameters and the terraform.tf file. Let's filter with the VPC we created and observe rest of the infrastructure. Go to the subnets. Sort it by name. Here we see 3 public subnets, 3 private subnets and 3 DB subnets that are created. All the details that we see here in these tabs are in line with what we have passed as parameters. Then go to the route tables. Here we see 2 route tables are created, one for public and the other for private. Let's quickly walk through to the rest of the stuff. We see Internet Gateway created, then DHCP option sets, Elastic IP for the NAT gateway, then the NAT gateway itself, network access control lists, and the security groups for ASG, RDS, and ALB. We will talk about the security group in detail once we get into ASG, ALB, and RDS. Then let's go to the RDS, go to the DB instances. We will see the demo RDS is created. Let's open that. We see that the endpoint is created. The port is 3306. Security group is attached. Subnets are attached. Let's quickly review other tabs. Under configuration, you see whatever we had passed in our terraform.tf file. The instance ID, the instance class, performance insights, etc. Maintenance windows and tags. Go to the EC2 console. We see here that 2 instances have been created using the auto-scaling group. Let's go to the load balancers. We see the DNS name is populated. Under listeners, choose view or edit rules. Open the target group, choose the same, go to the targets tab. Here we see 2 targets are registered by the auto-scaling group. Don't worry about the unhealthy status as of now. We will need to make some changes to the path and it will show as healthy. I will take care of the same later. Now let's have a quick glance at the auto-scaling groups. Open the auto-scaling group that was created using Terraform. Here under group details, we see desired and minimum capacity that we have passed as variables. We see here that the load balancer is also attached. Under activity, we see 2 instances have successfully launched. Let's have a quick look at the other tabs. After ASG, let's see what is provisioned in the launch templates. We see here all the details as expected. Let's go to the instances section. I will show you the user data. Choose any EC2 instance. Go to actions, instance settings, edit user data. Here we see the entire user data script if you remember that we had passed in the locals variable. This is an important line which will replace the RDS endpoint with the localhost so that our application connects to the RDS instance. Now let's try accessing the application. Go to load balancers. Under the description, copy the DNS name and paste in the new browser tab and hit enter. Here we see the default Apache landing page. Now let's check whether load balancing is happening as expected. We have a php.info page which gets all the information regarding the server and the PHP installation. On the top under system, we see the server DNS name. It is ending with 11.248. Now let's do a quick refresh and see what happens next. Now we see 12.180. So it is load balancing as expected on both the servers. Let's try accessing the actual application which is accessible on the path php-myadmin. Here we see the login screen. Now let's grab the username and the password for the application. Go to Visual Studio Code, open terraform.tf file. The username which we have set here is demo_user. Now we have to check the password which is generated by Terraform. Let's go to the RDS documentation and see the output parameter name for the password. So here we see db_instance_password. Let's go back again to the Visual Studio Code, enter Terraform output and the name of the parameter, that is db_instance_password, and hit enter. So it will fetch the value of the password from the state file. Many people might argue not to keep passwords in your state file, but as a best practice, initial passwords generated by Terraform need to be rotated after creation. Let's grab the password and enter in the password text box and choose login. As soon as we hit the login button, on the screen we see an error prompt stating failed to set the session cookie. This happens because php-myadmin is a stateful application and session information is generated on the server. On click of the login button, the request flows to the other server. To overcome this issue, we have to make changes at the target group level. Let's go back to the Visual Studio Code. Go to alb.tf. Scroll down on the line number 43. We see stickiness which we have commented earlier. I'll quickly show that the requests are flowing to both the autoscaling instances. If you see the server IP, it is changing. And that is the reason we are not able to log into the application. To understand more about the same, please learn about stateless versus stateful applications. Let's uncomment the stickiness parameter. Once done, execute Terraform plan to see what changes the Terraform is suggesting. So it's making changes to the autoscaling group. It says 1 to change. Now let's do a Terraform apply. It is acquiring state lock. Enter yes to give a confirmation. And the required changes are complete. Now let's go back to the application again and try logging in. Enter the username and password and hit login. So as expected, we are able to log into the application. Let's validate whether the request is flowing in only one of the server. So here we see 12.180 server. Let's do a quick refresh to see whether it remains the same. So what happens here is a particular client connects to a specific server whenever we run the load balancer URL. This helps to maintain the state in a single server and in turn allows you to log into the application. Let's check where exactly this change was reflected in the AWS console. Go to the target groups, select the particular target group, click on the attributes tab. Here we see stickiness type is ALB cookie and stickiness is on. Now let's see the security groups, what ports we have opened. To understand the network flow, we have 3 layers: web, app and DB. In the web layer, we have a load balancer. In app layer, we have PHP servers, and in the DB layer, we have RDS instances. So let's go to the security group of the load balancer. Go to inbound rules tab. We see a record for 0.0.0.0/0 on port 80. This is to allow all incoming traffic from the internet. Choose ASG/SG. Here we have whitelisted port 80, which is the Apache port from the load balancer via its security group. And finally choose RDS security group. Port 3306, which is the default MySQL port, is allowed from the ASG security group. Initially, when the application was deployed, we observed that the health checks were failing for the target group, even though the application was working as expected. So let's have a look how the issue can be resolved. Go to Load Balancer, Listeners, View and Edit Rules. Open the demo ALB TG. Here we see that the health checks are failing. Go to Health Checks tab. It's because the health checks are by default configured on the root path and our application doesn't have anything on the root path. That is var www/html. However, we have a PHP info file which can be utilized here to set up the health check path. So to add the health check snippet to our code, let's go to the ALB module documentation. Under complete ALB, you will get the GitHub URL. Open that and under main.tf, you will get the snippet. Search for health_check. Copy the code and paste it in our alb.tf under the target group section. Here on line number 47, instead of healths, replace it with phpinfo.php. Save the file. This file is generated in our user data script under the asg.tf file. Run the Terraform format command to format our code. And let's execute the Terraform apply. Again, the same procedure will happen. It will acquire state lock. Meanwhile, the state is locked. Let me quickly show you the DynamoDB table items. Go to the AWS console, DynamoDB, explore items, click on the table. We see here 2 records. Open the second record. Here we see the locking information. My user @MacBook has acquired the lock and the other record has the digest information. Now let's go back to the Visual Studio Code. Enter the value to give a confirmation. Let's refresh the target group screen. Go to Health Checks tab. We can see that the root path has been replaced with phpinfo.php path. Let's wait till the health threshold of 3 consecutive successful health checks. After waiting for some time, the health status was updated from unhealthy to healthy. I have already committed the entire code base in my GitHub repository. Feel free to fork the same and make changes to your repo. I will also include the link to the GitHub repo in the description box. Thank you so much for watching till the end. If the video was helpful to you or if you have any queries or concerns, please let me know in the comment section. Thank you and take care.